everybody. So just a little announcement. Tomorrow afternoon, we're going to swap the order of the two lectures in the afternoon. So tomorrow is 2 Isabel lectures and 2 Ibu lectures. The afternoon lectures is now going to be Ibu at 2 and Isabel at 3:45. So just to let you know. And now we are going to conclude our series on scattering with Cliff.
So, welcome back. This will be the last lecture on scattering amplitudes. I'm going to finish off what I was saying about double copy in color kinematic duality before elaborating on some, I guess, other structures and other explanations for things we're seeing. What did we see in the last lecture? I showed you how any particle gluon scattering amplitude can be taken, arranged in a certain way, such that when you square them in a very precise fashion, you get the amplitudes in Einstein action expanded with gravity. Okay. Now, as I said before, there's actually a... Yeah. That's not me. Not the strange noise. In addition to your usual strange. It's on top of the strange noise. Yeah. Already on top of it. Is that cool or is that okay? No noise. Okay. Let's start moving and see. Yeah. Okay. Let me know if it's difficult to hear me. So I also commented before that there's actually many different guises for this kind of squaring relation. I want to show you briefly the case of pions. Okay. Nonlinear sigma model scattering amplitudes squared, which we'll see give amplitudes in the so-called Galilean. Okay, so we'll work through this example relatively briskly now. Okay, so of course we didn't compute pion amplitudes here, but I'm just going to quote them. You can easily use whatever Feynman rules you like to do so. But the idea is the following, and as promised, none of the rules will change. The exact same rules that applied to gauge theory and gravity will apply to these scalar effective field theories. The idea here is I want to write my pion amplitude exactly in the same way, Ct nt over t, Cu nu over u. Okay. Now, of course, you'll immediately note and realize that for pion amplitudes, right, if you think about the usual canonical representation for pions, which is a sequence of operators that look like d pi squared pi to the n, there's no odd point interactions. So it's even a little confusing why I'm writing poles here, right? Because there are no S or T or U channel poles at 4 point. It's just a contact vertex. D pi, 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 right? Now, that's fine though. We already encountered this for Yang-Mills. The point here is that even though this function ultimately has no singularities, we can put factors of S, T, and U in those numerators in whatever way we like, provided when they cancel, we get the correct answer, okay? Any arrangement you like will work, okay? So let me choose one. Okay, so in fact, let me actually, you can anticipate that I'm going to be using different types of numerators soon. So let me label this numerator, NLSM, nonlinear sigma model. Okay, so we can define the NLSM numerators in the following way. Again, you shouldn't know why this is true, but my claim is that if you choose these, you will get the amplitude that you would compute by other means. NT, NLSM, S squared minus U squared, and NU, NLSM equals U squared. Okay, so you can kind of see already how poles will cancel. This S will cancel one of these S's, U will cancel one of these U's, and a T will cancel this S plus inside this factor. So if we, again, just to maybe check, if you just plug these expressions in, what you'll find is the honest to goodness known expression for the pion amplitudes, where there's 2 derivatives in the U, 2 derivatives in the S, and then the CS and CU encode all the flavor structure. Okay, so I'm calling them color. It's a kind of a abuse of nomenclature, but we don't want to have to keep saying flavor instead of color. So indeed, this is the global symmetry I'm talking about, but it has all the same kind of tensor structures, which is why we can do the same thing. Okay, any questions about what's happening here? Okay, so what do we do? Well, the rule is, well, you can check just by I, ns plus nt plus nu equals 0. Okay, they sum to 0. The kinematic Jacobi identity is satisfied in the chiral Lagrangian. You compute this any way you like, this will be true. Okay? What this means is we can immediately start double copying. To do that, I just square each of these terms. Okay, so in particular, when I say square, I mean take this CS-CTCU structure and throw it away and put 2 copies of NS instead. So we get s to the 4th over s plus s squared minus u squared over t plus u to the 4th over u, which is minus STU, which is precisely the 4-particle amplitude for the Galilean. Yes, question?
There's some theories it can't be double, right?
Yes.
So is there a clear way to see from the Lagrange picture or from the color kinematic picture
Good.
when you can't double?
Thank you. So you're jumping ahead, but the short answer is no, because we don't understand the underlying mechanics here. I'll get into this shortly, but you could say, would this work for like a random other theory? Let's say I started adding higher derivative corrections or this or that. There is no universal answer because we don't actually understand the underpinnings of why this is true. But I'm going to kind of litigate that question a lot more in the second half of this lecture. So just wait a little bit. Yes? Yes. So any choice you make, any gauge you compute in, these will change, but in a way that is different in the same way as in Yang-Mills. So the numerators can change, but the amplitude will stay the same. And for whatever choice you pick, when you square it, you'll still get the same answer. Okay. Now, I'll comment on something here, which is there's a couple surprising things already, which is it isn't even obvious that this thing would be permutation invariant, like STU invariant, because like the numerators themselves don't have that symmetry. I like broke that explicitly just by my choices here. Of course, you can make a choice that preserves it, but I chose to not. And in spite of that, it gives a final answer, which is the correct, fully symmetric in all external legs amplitude for Galilean, which is a single scalar. Okay, so that, like, if you like, this is kind of the analog of what was surprising for gravity. When we square numerators, there's no reason that should be gauge invariant. You don't just do this. So I mean, hopefully this is obvious. Take Feynman rules in whatever gauge you're in and just start squaring certain Feynman diagrams. You will not get sensible things. So the question is not that we landed on a consistent spin 2 theory from a spin 1 theory and we're surprised. Of course, we know that spin 2 theory had to be gravity. The surprise is that we had an operation that even gave a consistent answer. Okay, that's the surprise. Okay, so this is, I probably shouldn't use this board because I should use the one behind it, but that's okay. So this is the Galilean. We can now mix and match. Okay, so let's do one last example. Okay, so one last example is let me take NS for the NLSM over S, okay, and then multiply by NS for Yang-Mills. Okay, we computed this last time. I didn't put the superscript because we were just doing Yang-Mills, but those numerators we computed previously, put them here. Take these NLSM ones, put them here, and then sum. Okay, so, okay, T and U, okay? What do you get? You get an amplitude, which is precisely 1, 2 squared, 3, 4 squared, which is actually the amplitude for Born-Infeld theory. Okay, what was Born-Infeld theory? Maybe I can just remind you in case it's not in your mind. We talked about Dirac Born-Infeld theory. Born-Infeld theory is a theory of a scalar, of a vector. So it's if you like, it's a nonlinear extension of QED, which has an action that looks roughly like determinant of eta mu nu plus f mu nu minus f mu nu. So there's some signs and factors here, but it's an infinite expansion in powers of f. Okay, its dimensional reduction is that scalar we saw in the last lecture. Okay, and here we've landed on it. Okay, now this is all true at 4-point. 4-point simple, so maybe it's not too surprising. The more surprising thing is that if you go to higher and higher point, this is just true for the full S matrix for any numbers of particles. These are proven facts. Okay, so what we have is a machine now, which lets us compute from you know, if you like, more basic objects, the full S matrices for other theories. And we can even draw, maybe just to be a little pedantic, a multiplication table for theories in this way. Okay, if we like keep track of like what we multiplied. What are the theories we've been talking about? I talked about biadjoint scalar theory, the simplest theory. I talked about pions and LSM, and I talked about Yang-Mills theory. Okay, and now I can imagine multiplying any one of them with each other. So biadjoint scalar theory, and what do I mean by when I say multiply? By multiply, I mean take a color structure and like replace it with the kinematics of such a theory, okay? So by this I mean, in the numerator I want to put the Yang-Mills numerator and a second copy of the Yang-Mills numerator. In this case I get GR. Here I get Born-Infeld. This is of course a symmetric matrix. I'm just rewriting what we just saw, the Galilean. And we can think of the top row as like the identity, which is pretty trivial, but I feel like I should write it. So, okay, there's a bigger space of these if you add supersymmetry, if you add matter, okay, you add adjoint quarks, you can add fermions. I mean, I'm not going to be able to go through the list of things, but for instance, if you take a pion in the NLSM, you double copy it with if you take a pion in the NLSM and you double copy it with a gluino in an N=1 gauge theory, okay, so one's a spin a half, the other's a scalar, you'll end up getting the Goldstino of Volkow-Alkolov theory for a spontaneous supersymmetry breaking. If you take a gaugino and a gluon, you'll get a gravitino, okay? So like there's this whole like multiplication table of particles, which is very reasonable. If you just kind of count their spins, you can figure out who maps to who. But all the non-triviality is the fact that we picked out this particular theory of a massless spin 1 vector here, which is born in Phil. Okay, any questions about that? Yes?
So is this true for any endpoint amplitudes at tree level?
Yes, this is a proven fact for all n particle scattering amplitudes for any n at tree level, yes. Yeah, yeah, I haven't proven it here, but it has been proven, yeah. Good, yes?
Is there any sense in which you could add some of the ones that appear as products and multiply them further with some?
Is there a triple? Is there a triplicate?
Sure. Yeah.
Okay.
Because this is not a closed group multiplication table.
Yeah. Good. Could you keep going further? So somehow intrinsically, if I start with bi-adjoint scalar, 2 colors, you're kind of naturally always going to be multiplying 2 objects. But you could, I think, probably ask about if you had like a tri-adjoint scalar theory and start adding these factors. It's not obvious to me that it would be consistent, and for various reasons that, for instance, there don't exist massless spin 3 consistent self-interacting theories, I would suspect that things will go wrong. But I don't think anyone's actually tried that, like not bi-adjoint, but like multi-adjoint scalar. But it's something you could try. But nothing's guaranteed. So hopefully it's clear, like you can't just do this with random old theory. This is something special, okay? All right, so yes, yeah, sorry. Very good. So I'll get to that maybe in like 15 minutes, okay? To get to ADS, we first have to understand what's happening. And yes, there do indeed exist double copy structures, which I believe are like continuously connected to these. And those structures don't act on amplitudes, but on Witten diagrams or boundary correlators, okay? I may not even get to that, but if I don't, we can talk about it. But of course, before you can go to curve space, you need to like figure out what's going on here, which I will do shortly. Yes, lots of questions. Good. Yes.
Do they just go up to a certain number and calculate all this stuff?
No, that wouldn't be proving. That would be checking. Yeah. No, it's proven because there exists these ways of constructing amplitudes at all orders in perturbation theory at tree level, which are recursion relations. So in other words, you can check that a graviton amplitude satisfies BCFW recursion. You can build it using the double copy and check that it satisfies the same recursion relation. So indeed, precisely because we have all orders in n ways of like defining this whole procedure, we can check it. But excellent question, yeah.
Are there any examples of, say, fermionic theories which double copy to a, say, vector theory?
Yes, yeah, definitely. Sorry, are there theories where there are fermions that square to give vectors? Indeed, so I think there's examples where you have well, it's almost like QCD, a fermion, adjoint fermion coupled to gluons, which you square, and you end up getting vectors coupled to gravitons. So everything you think will happen, like the spins will double, everything doubles because of little group, of course, it had to be, okay? But then the fact that it's a consistent theory is the surprise, yeah. You need to double copy everything. Yeah, that's right. So in some sense, yeah, everything in the multiply gets multiplied together. Good. Now we have this, set of theories I've described. Gravity is at the top, and it's the square of other things. But there's another kind of amusing structure I just wanted to highlight. Maybe I'll go through this a little bit fast, which is that these are connected in other ways. Okay, and my mantra for this is that gravity is the mother of all theories in a super concrete way. Okay, let's say someone handed you the full tree level S matrix at n particle scattering for all graviton amplitudes, okay? They give you the whole thing. You're just handed it, and Oracle hands it to you. You can sculpt out from this every amplitude I just wrote here, Bornenfeld, Galilean, pions, Yang-Mills. It's sitting inside here. Okay, so here's the drawing I'll draw. Okay, I'll make this precise in a second. Okay, let me just do it this way. So Yang-Mills, scalar. Okay, and there's a way of extracting everything from it. They're linked in a different way. Pions are connected to gravitons through this chain, which is an extremely simple mathematical procedure, which I'm going to show you now. Yes. Oh, sorry, Bornenfeld. Thank you. Yeah. Thanks for pointing. Any other questions or board errors? Yeah. Thank you. Cool. So there's a name for these. We call them unifying relations. And as you can anticipate, they're going to be transformations that let us take an amplitude to another amplitude. Okay? And here's how it works. Okay? So I want to take an n-particle scattering amplitude, and I want to think of it abstractly as some function of Mandelstam invariance. Pi, Pj, Pi, Ej, Ei, Ej. Okay, so I'm not even going to be using spinor helicity. Okay, let's work in general dimensions. But I want to think of it as a function of these scalars. Okay? Now, if you do that, that's fine and good. I'm having polarization, so we're kind of back to like lecture 1, where I have to introduce ward identities. You know, there's redundancy. Let me just deal with that. How would you deal with that, thinking of this as an abstract function of these scalars? Well, let me say it this way. If I wanted to take the n-particle amplitude and send Ei goes to Pi, okay, I can write that actually as a differential operator. This is clear. So here, implicitly imagining n as a Yang-Mills scattering amplitude. Okay, but the idea here is I'm going to hit this with a differential operator, call it like script Wi, which applies the ward identity to leg I. Okay, now what is this operator? I can be very explicit here. The ward identity on leg I is the following. Okay, let me write it and then I'll explain it. Okay, what am I saying here? So V is a vector which is summing over all the vectors in the amplitude, all the polarizations, all the momenta. Okay, just summing over every possible D vector that's in play. This is a differential operator with respect to the Mandelstam invariant V dot E. Okay, and this is just multiplying. Okay, so you can see what this is doing. This is just a dumb way of writing the ward identity because it takes any place that is contracted with a single polarization and it replaces it with that polarization having Pi. That's all this is doing. Okay, so this is just implementing the ward identity as a differential operator. Good. So that's the kind of first operator we need, which is the ward identity. The second operator is kind of even more trivial, but I'm going to define it anyway. Just it'll help us think about this, which is momentum conservation. Okay, if you like, I'm kind of imposing kinematic and on-shell consistency conditions, but as differential operators acting on functions. So let me define this thing called PV, which hits AN and gives 0, where, I'm going to make it script, where PV is nothing more than sum on PI V. Okay, so all this says, this is P, and this is script P. The idea is this operator PV is just the vector V, which is some vector of your choice, dotted into every momentum and summed. Okay, this sums to 0. So if you like, I think of this as an operator that annihilates the amplitude. Okay, it's a total momentum conservation as an operator statement. Okay, any questions about this? Okay, it's certainly somewhat needlessly formal, but I'm introducing it. Yes.
In that operator, like del by del V.
Yeah.
So we are summing over all possible momenta, but these momenta are related to each other.
Yes.
Does that depend on what sort of representation you
Very good. Yes. So you would worry about that because I could use momentum conservation to move things around, which is why we should see whether these commute. Yes. So indeed, that's exactly the right question. Is it consistent with different ways of rearranging the momenta? So let's check that. Okay. So in particular, you can just look at. Okay. So there's some. So let's look at the algebra, the commutator algebra of the system. Okay, obviously, total momentum conservation commutes with it because it's a number. It's not even a differential operator. We look at the ward identity for leg I, the ward identity for leg J. Okay, I'll skip the calculation, but it's also 0. And then lastly, you could ask, what about the ward identity for leg I and PV, okay? Which would be another way of saying, let's say I just added a term with total momentum conservation to my answer and check the ward identity, is it still satisfied? And what you find here is that this is equal to delta VEI P PI, and this annihilates the amplitude. So it doesn't commute, but it commutes up to an object which annihilates the amplitude anyway. Okay? So things don't have to strictly commute, they just have to commute up to things that will be annihilated. Okay. Now why am I going through this? Well, let's say you wanted to build a differential operator that makes amplitudes out of amplitudes, or makes physical things that conserve momentum and which satisfy ward identities and generates new ones. Okay, well, you want to build an operator which we'll call T. Okay, so this is T for transmutation, transmuting amplitudes to amplitudes, such that it commutes with both of these operators. Okay, so okay, so if these are 0, okay, if it commutes, and whenever I say commute, I mean commutes up to things that will be 0 once you hit an actual amplitude, then the following is true. Okay, this is just me saying what I just said here. Okay, take an amplitude, take some physical scattering amplitude, and hit it with this thing. Okay, I made a new object. You could ask, does this thing satisfy the ward identities? Does this new thing satisfy momentum conservation? Well, yes, it does, because these commute. Okay, so since this is this, WIAN, this is 0, okay? And similarly for momentum conservation, okay? So if you can build something which commutes with these, then that object will take gauge invariant things and make other gauge invariant things, okay? Now you can systematically bootstrap such an object. And we're gonna do it the way we do everything. Actually, I won't go through the details of it, but I can point you to a paper if you like, but, oh yikes, that's, what that is. You can, for instance, let me write it here. You could write an ansatz for T, okay? So for T, I could say, write this as Aij times dd PIPJ plus Bij times dd PIEJ. Okay, you can see what I'm doing. I'm just writing a differential operator, I'm writing an ansatz for it, and searching for one such that it will have these commutation relations. Okay, now let me just skip to the end and tell you what the operators are, because they're very simple. Okay, this really didn't seem to work out here, so. Okay, you can build such operators. Okay, so here's one operator. Okay, keep in mind that the indices will be different for each of these. Let me write down the operators, and then I'll talk about them. Okay, so this is a differential operator with respect to EE. These are a difference of differential operators with respect to P dot E. And last but not least, I'll call this TI, which is the sum on J of PIPJ DDPJEI. Okay, these are just a bunch of differential operators, okay, from which I can build amplitude to amplitude operators. Okay. Let me give them a name. Let me call this, for reasons that maybe not be totally clear, I'll call this T color, which is just made up of products of these. Okay, so in fact it's, okay, there's many ways of doing this, but here's one. It's a single TIN, I equals 2 to n minus 1 of T I minus 1 I n. Okay, the 3 index one and the 2 index one. Okay, so it's a product of these 3 index transmutation operators, and then one last product with 2. Okay, and then there's another one I'll call T derivative, which is a little similar, almost looks the same, except the product from I equals 2 to n minus 1 is just of Ti. Okay, I'm clearly pulling this out of a hat, but what I'm telling you is that these operators commute with ward identities and momentum conservation. And they're a specific combination which turns amplitudes into other amplitudes. Okay, now I should say, why was there any, like, why did I have to do any like fine choice of which operators to choose? Well, clearly I can build lots of gauge invariant things from a gauge invariant thing. I could take a gauge invariant object, multiply it to the 7th power, that's still gauge invariant, but it's not an amplitude. Okay, so there's something a little surprising that like there's operators that just spit out gauge invariant things that also happen to be amplitudes. And those things are all these theories. Okay, so if you don't worry about where the backstory of where this came from, I should say this is proven, of course. At n particle scattering tree level has this property. It's just a fact. It lets you take GR amplitudes and hit it with this color differential. You can think of it as like, compute any way you like the graviton scattering amplitude and take derivatives with respect to Mandelstam's in this way. You'll get Yang-Mills amplitudes. So this is the color. You do it again, you'll get biadroit scalar theory. Okay. If instead you choose to hit it with the differential operator, which I call deriv, because it's adding momentum, you get Born-Infeld. And so on and so forth. So kind of depending on which way you're moving in arrows, you'll make it to pions or you'll make it to the Galilean. Okay? So this is what I meant by you can literally sculpt out pion amplitudes from graviton amplitudes. Take your graviton amplitudes, you could do it two ways. You could go one way or the other way, it doesn't matter, and you'll like actually just compute pion amplitudes. Okay. So we call that transmutation. It's a very slick way of just getting amplitudes in other theories. So now you can see this is like at least a machine for spitting out all amplitudes in the system. Start with Yang-Mills, easy to compute, go get gravity, and then everything is yours. Okay? And this is literally how I personally compute amplitudes, because it's easy. I just have to build it once and then take derivatives. Okay, any questions about this? Yes?
Is it clear that the amplitudes that we get after acting on these operators is also Bose symmetry?
It's totally not obvious from the differential operator. Good, thank you. So the question was, is it obvious after hitting one amplitude to another that the answer you get is Bose symmetric? It looks like I've made 1 and n special, because I did. But you could choose any two, and it still gives a Bose symmetric answer. So indeed, the differential operators themselves do not manifest Bose symmetry, but the final answer, since I'm telling you it is the amplitude, does. Okay? It's a very common feature, which is just like in double copy. The intermediate steps were not even Bose symmetric, but bam, in the end, it all works out. Okay? Now, you could easily ask now, why is this true? Okay? I'm not going to talk too much about actually this specific construction here. There's actually ways of thinking about this as a kind of exotic dimensional reduction. But I wanted to take this as an opportunity to like step back. Okay, there's clearly structure in play. Wouldn't it be much better and much nicer to actually have some like field theory, Lagrangian, if you like, way of thinking about this? Is this the only recourse to kind of manipulate amplitudes? And this leads me to like my final kind of chapter, a longish chapter in my last lecture here, which I'm going to call Beyond Scattering Amplitudes. Okay. Now, what do I mean by that? Well, everything I've said in this whole series of lectures was about flat space on-shell scattering amplitudes, which is, of course, not the totality of things that we care about as physicists. Okay. But I want to mention a couple outgrowths, and then I'm going to finish with some QFT explanations right at the end. Okay. So this is beyond scattering amplitudes. This first kind of story will be more story in words. Okay. There's a very clear question that I think many of you had after I said gravity is the square of gauge theory, which is what about curved backgrounds? Okay, what about black holes? Big things like that. Clearly something is true in all orders in perturbation theory. For classical flat space physics, you might think or guess that something should exist. Back when I taught this set of lectures in 2016, there was something that was kind of connected to that idea, which is called the classical double copy. Classical double copy. Let me tell you what it is, basically, okay? As quickly as I can. If you take the Schwarzschild metric, but not in usual Schwarzschild coordinates, and not even most coordinates that people have thought about, but in so-called Kerrschild coordinates, maybe a slightly less studied choice of coordinates, you can write it in a very interesting way. Okay, so I just want to emphasize, there's an 80 mean u here, which you may think that I'm doing perturbation theory or something, but this is just a way of parametrizing the Schwarzschild metric. This phi here, so actually let me tell you what k is. K here is not just some constant. K here is 1 r hat. And phi is 2gm over r. Okay, Schwarzschild radius divided by r. Okay, now you might immediately see this and be like, wait a minute, what's going on? This thing truncates at linear order in G. Schwarzschild metric is all orders in G. There's all this like non-perturbative in G Newton physics. This is a gauge where all of that is just squashed into a linear term. That's what's fascinating about Kerr-Shield. It like linearizes the solution. So this is the full GR solution. This is the full Kerr-Shield solution, for a full Schwarzschild metric. But it can be written in a way where just mechanically it has a single factor of G. That's already kind of interesting. Now the observation of, I mean, it's almost, it seems kind of obvious if you just look at it now. If you look at just the structure of this, the observation, this was this beautiful paper by Donald O'Connell and Ricardo Montero, and then many others have done really interesting work following up. Just the realization that this is, this is gravity, and if I wrote down a Coulomb solution, okay, well, phi equals alpha over r. Okay, it's just kind of like, look at the left-hand side, look at the right-hand side, they're very similar. Okay, that probably doesn't do justice to the correspondence, but it's essentially, these look shockingly, strikingly similar. Certainly this must be some classical version of this. Now, all the way up to 2023, I think we understand where this is coming from, and it follows arguably in large part from the 3-particle amplitude squaring. Okay, it is precisely a descendant of the properties of 3-particle couplings. But at least for just general, like, if you like, some random classical GR solution, we do not know how to do this copy. Okay, so for instance, if you had 2 black holes, where we don't even have a classical GR solution, like analytically, we have no idea what this mapping would be. Okay, now that's why in my old TASI notes, I put something, some like offhanded comment, like, oh, this is kind of a hallucination, maybe someday we'll use for gravitational waves, but that actually happened. Okay, so in fact, it happens very swiftly, and I want to tell you about that story briefly, very briefly. So what occurred was we kind of stepped away from this kind of very ambitious goal of just taking every classical solution and copying it, because we clearly don't know what the rules are. Okay? Instead, we returned to perturbation theory and thought about the fact that you can do perturbative calculations relevant to the black hole binary inspiral problem that LIGO cares about. Okay, we usually think of there being, there's 2 black holes, right? They're in orbit with each other. There's certainly the most interesting regime is when they're, merging, coalescing, clearly strong field, something you need numerical relativity for. But in the early inspiral, there's famously perturbative methods that have existed for like 100 years to study this. One of those methods is called post-Newtonian. Yeah, we're not going to do any of these calculations here, but I wanted to give you a lay of the land. Post-Newtonian, or PN, which is a statement of a perturbation theory in gm over r, which is of order v squared, which is much, much less than 1. Okay, you can think of it as slow-moving objects in a virialized system. V squared is of order this. Okay, in terms of scales, it means the 2 black holes are much farther apart than their Schwarzschild radii. Okay, so they're distant from each other and kind of slowly moving. Now, post-Newtonian theory would just compute in both of these couplings order by order, okay, because they're of order each other. And that's a very fruitful and powerful program, which has really been the engine of what folks have, at least part of the engine of how they build waveforms, which is a combination of these post-Newtonian, numerical relativity, and ring-down type calculations. Okay, but you can see as a relativist, there's something funny about expanding in v squared, right? Okay, like let's compute the v to the 4th correction. All right, let's do the v to the 6th correction. There's something intrinsic to the way we think where it's like, wait, can't we just repackage that all together? And indeed, there is a way of doing that. It's now been dubbed post-Minkowskian PM, okay, which is just expansion in G, if you like, just the G side, but all orders in V. In our field, we call that perturbation theory in G Newton, okay, just compute in G. Okay? And so let me spare you the details, but the upside is this. This is the set of calculations that happened. we didn't compute in gravity. As I said, don't compute in gravity. It's a bad idea. We computed in QCD, okay? We took QCD amplitudes, Yang-Mills amplitudes, for massive states scattering through gluons, okay? Then we looked up the cheat code and squared it to get gravity. And what that means is two massive particles scattering through gravity. Those massive particles are precisely the description that you'd use in, for instance, post-Newtonian of like massive point particles interacting gravitationally. So we essentially computed to high, or me and others have computed to high orders the scattering amplitude for two black holes. Okay. Now, naturally, you should also wonder, wait, black holes have finite size. How are you doing this? Well, you can add those finite size corrections. We did that too. So we can also scatter neutron stars. We also did that calculation. The point is, you can add those bodies and compute to very high order using these tricks the scattering amplitude for black holes. Now, of course, LIGO doesn't care about the scattering of black holes, because black holes don't scatter, they're an in-spiral. But that's okay, because you know from classical mechanics that if you know the scattering angle between two bodies, you can engineer the Hamiltonian from which it came. Okay? So I won't do this here, but basically the idea is that once you've computed an amplitude that depends on some center of mass, momentum, and a momentum transfer, you can get from it a Hamiltonian, like literally a point particle Hamiltonian, governing the two black holes. Okay, this is called a matching calculation. It's done in effective field theory all the time. We basically borrowed methods from HQET and NRQCD. But the upshot is that we could give folks who are interested in gravitational waves in their currency, their native currency, which is Hamiltonians, expressions that had never existed before. So what I'm saying is that now, as of today, and as of our original calculations, the state-of-the-art calculations in post-Minkowskian, that is to say, highest order in G, all orders in velocity, are done using amplitudes methods, okay? By squaring, but also using EFT. And it's been very cool because at first, of course, we went to the community and they're like, who are these strange people with saying these weird words, double copy this, unitarity, mass confusion, lots of complaints. But in the end, you know, we're all on the same team now. Everyone's pretty happy. Postdocs are being shared between groups. It's pretty interesting. Like there's been a lot of cross-pollination. We've all learned a ton. Now in the end, though, like what's funny now is that kind of the hardcore gravitational wave calculators are like using integration methods now from amplitudes, like unitarity methods. Like these ideas have all seeped in because it's just powerful, and if it's practically useful, we should use it. But that's a cool story here because, you know, if you look at the lineage of the tools we used, it goes all the way up to string theory, if you really think back. It was mentioned earlier that KLT was like the original kernel of the double copy. That's string theory tools all the way down to black hole physics and celestial mechanics, which we ended up doing a whole bunch of, all the way down to a Hamiltonian, which now the group of Alessandro Bucano and others who build the waveforms can like put into a computer and compare against numerical relativity. So it's pretty exciting to see that kind of start to finish story. So this whole thing, again, it happened all after the last time I was at TASI, but we're still in the middle of this. This is now a cottage industry in amplitudes. People are now computing conservative radiation reaction dynamics, self-force, like all these things that are like really kind of hardcore and connected to the experiment. We're hoping to maybe make an impact. Some impact has been had, but it's still really early. Okay, so that's why some folks are pretty excited about it. Okay, so that's all I want to say about gravitation. Oh, yes.
What are massive states on the Yang-Mills side or the blue one?
You can really make them massive scalars. Oh. Yeah, okay. That's not me. I'm always worried it's me.
When you're double copying Yang-Mills.
Yeah. So it depends on the state you're looking at. So if you care about spinless black holes, which was our original calculation, we make them scalars because they have no spin. If you want them to spin, add spin. Yeah.
Also for when you're considering asymptotic states in Yang-Mills, do you have an additional scale, lambda QCD?
So this is a perturbative calculation. So indeed, if you really cared about confining Yang-Mills theory, you know, you have a mass gap, much more complicated. I'm talking about perturbative QCD, which is the regime within which the double copy applies. Hopefully that was clear. Perturbation, tree level, you know, one loop, two loop, and so on. So in fact, we've somehow got a win here. Thank goodness it worked for perturbative QCD, because you can square it to get gravity, which is always perturbative. Yes?
So Hamiltonians are not gauge invariant, right?
Nope.
So how do you go from a gauge invariant point
Good. So Hamiltonians aren't gauge invariant, Lagrangians aren't gauge invariant, equations of motion aren't gauge invariant. Hopefully I shouldn't say not gauge invariant, but not field basis invariant. There's no invariant notion of them, okay? Don't want to offend anyone. But they're not invariant, totally invariant objects, so choices have to be made. And that's just straight up what you do. You write a Hamiltonian in harmonic gauge, isotropic gauge, whatever gauge your friends like, and then you do the matching. So in some sense, we had to like shed our desire to keep everything invariant in order to have a conversation with people, which is okay. So we want to be useful. So we just picked a gauge and then did the matching. Yeah. So in other words, there's many Hamiltonians that give the same A, but we picked one that they liked and then gave it to them. Yeah. Yes? Oh.
When you go from GR and you add these operators to get how do you get the color structure back?
Excellent question. I was very fast with that. Thank you for bringing that up. So maybe it's gone. Okay, so you'd be like, wait, how did I go from GR to Yang-Mills? How did FABC become born? I should have said that the Yang-Mills amplitude I get are the so-called color stripped or color ordered amplitudes. So it's the basis of amplitudes after the Fs have been stripped off. It has all the same information as the full amplitude. Yeah, thank you for asking the question. Okay, good. Now, let me finish. How much time do we have? Like 10 seconds?
No, you have 35 minutes.
Awesome, perfect. All right, time to write. Good. I thought you were gonna say 35 seconds, and I was gonna I would just drop the mic and just left. Yeah.
There's a student who's trying to ask you a question.
Oh, sorry. Okay, yeah. 35 minutes later, yeah.
If you have spinning black holes, how do you deal with the fact that your particles are some quantized spin black holes?
That is a great question. Okay, so this is something that people are trying to. What was the question? Yeah, sorry. I should repeat the question. If you have spinning black holes, which are that's classical spin, how do you think about this in terms of these point particles, which clearly have like intrinsic quantum spin? Okay, so this is something that's like already being closely understood and litigated. It's actually complicated. There, of course, isn't some continuous spin parameter in QFT for particles. So what's usually done is if you care to some order in like your spin or spin orbit couplings, you can put in a vector or like a spin half particle and get those kind of low order spin orbit type operators. You want to go higher and higher order in spin, you have to add bigger and bigger spin particles. But it's actually still confusing. Like we're still slightly confused about that like classical to quantum transition. So I would say that's still ongoing research. Not something I personally work on myself so much, but I think it's a really interesting question. Yeah. Okay, cool. So if there are other questions, why don't I try to give you some answers rather than just like confusion and structure, okay? Why is this true? Okay, maybe I say it that way. Why is there a double copy? Why is there color kinematics duality? Okay. Now, on occasion you might ask someone who thinks about this and you might ask them this and they'd be like, well, what do you mean why? We proved it. I proved it at n particle scattering with recursion relations. What's to not understand? It's a mathematical identity that's true. Okay? So sometimes that's an okay answer because maybe that intuition will come later. You only have a calculation, but you'll find the words around it. But I would say that we don't even have the calculation. Why do I say that? Well, whoever told you that they understand the double copy, I want you to ask them the following questions. How does your proof generalize or not generalize in curved spacetime? Okay, so they have to be able to either say it proves that it doesn't work in curved spacetime, or they should say it does work in curved spacetime. They're not allowed to say I don't know, because I used Mandelstam invariance. Okay, that's not an okay answer. How does it work in any other, let's say non-perturbatively? Okay, not in perturbation theory, but let's say you have a theory where not like as what most of this workshop is about, non-perturbative physics. Okay, out of perturbation theory, is this true? How about something even more innocuous? Higher dimension operators. Okay, by this I mean higher derivative corrections you could add to any of these theories. Now, I should say, I'm not saying that there's been zero work on these. There's been tons of really super interesting work kind of eating at the sides of these and trying to piece this together, but no one has a proof that explains which higher dimension operator is like full stop, double copy. Like there are very interesting suggestions and I think really systematic paths here, but nothing that we would say, oh, we've proven it. And here's even a basic question, classical solutions, just generic classical solutions. Can I take numerical relativity? Is it the square of something or not? That should be a yes or no question. Now I would say that if you really understand why something is true, you should be able to tell me why it either is true or not true in these contexts. Like for instance, symmetry conservation laws. We understand those. Those are understandable. Which is why if you ask me, how does your conservation law work in curve space? I can tell you, I can tell you when it's, I can tell you in every context when I understand something, whether it's true or not true. And if it's not true, why it's not true. But for double copy, we have, I would say, to 0th order, no idea why. Okay? I feel like it's an open question. Now, let me tell you about the progress that's been happening to disentangle this. There are some examples where like a Lagrangian level understanding or like a field level understanding exists. Okay? A large number of those, certainly earlier, were integrable or intrinsically topological theories. Okay, so I've caught the eye of some of you, I'm sure. What do I mean by that? So very early on, in one of the most, again, beautiful papers on the subject by O'Connell and Montero, they studied self-dual Yang-Mills, okay? A very special subsector of Yang-Mills with only plus helicity or only minus helicity gluons. And they found that self-dual Yang-Mills, squared to gravity, self-dual gravity, and they could understand it. Okay, at like the level of a set of equations of motion, and there was a kinematic algebra. Okay, it's a cool story, not one that I have time to talk about. Okay, another example, which was actually from last year, is actually Chern-Simons theory. Okay, Henrik Johansson and his collaborators noticed that the Chern-Simons action. Okay, we've all stared at it for years. If you just write down its Feynman rules and look at them, you'll realize that they have a kinematic Jacobi identity satisfied. Okay, and that's pretty remarkable, just out of the box. I think it's in the Lorentz gauge that that's true. But if you pick a certain gauge, Chern-Simons theory has this property. Okay. Now, of course, one downside of these is that there's no degrees of freedom in these theories. The S matrices are vanishing. That's not super exciting in some sense. I mean, I think it's very interesting, but I will, as maybe a pushback, I'll say that if your scattering matrix is 0, it's very easy to double copy. Okay. Take your numerators, set them to 0, square them, I get 0. We did it, guys. Okay, that's harsh. It's harsh to say, but you know, it's better. You know, I like degrees of freedom. I'll say it in front of you. Yeah, I like non-topological quantum field theories with zero form symmetries in a very narrow focus on 3 + 1 dimensions. Yeah, I'm in this very tiny field that studies this. No, but in all seriousness, like, okay, it would be great to have other examples, right? Okay, so let me tell you the example which is dear to my heart personally, which is pions, and I'm going to give the explanation for pions in general dimensions. Okay, and by the answer I mean, what's happening? Like, what is the mechanics of why this is working? Okay, and just to remind you, the statement was, maybe it's sit behind this board. Yeah, okay, just to remind you, okay, this won't help. The statement was that if you take pions and square them, you get Galileans, okay? Let me try to explain that to you. I don't have an explanation for gauge theory and gravity. I may never have one, but let me tell you my understanding for pions. At the level of fields, okay? We're returning, as I said before, to the dark side here, okay? So, NLSM, Bohr-Ninfeld, and Galilean. These are the theories that kind of partook in the double copy. Let me explain what the mechanism is. It's very simple. I can say it in words, and then we'll do it. Take everything with a color algebra. Take a theory that has a color. A, B, C indices of some kind. Particles in an adjoint, fields with adjoint indices. There will be structure constants, Jacobi identities. Everything like that's important about that theory will depend on those identities. Okay? So there's some color algebra structure. And send it to another algebra, which has all the same identities. Okay, I could say this many ways, but I'm going to call it the diff algebra. But it's more accurate to call it the Lie bracket, okay? The algebra of vectors, like just vectors, commuting vectors, okay? I'm just calling that because those look like gauged translations, but send color to diff. Okay, and I'll be very concrete about what I mean in a second. Now the point here is that this is like, this has commutators, Jacobi identities, everything's satisfied on its own. But what it effectively does is take numbers and send them to derivatives with momenta. Okay? My claim is that all these operations, at least for this sector of theories, is this operation. Okay? And let's do that at the level of fields. Okay? So let's stop looking at amplitudes for a second, and let's look at a Lagrangian. Well, yeah, the broad name for it is kinematic algebra when there's a question mark. But I'm telling you, the name for that algebra is the algebra of brackets, of the Lie bracket. So yes, I should say, in case the nomenclature wasn't clear, like when we say kinematic algebra, it's like what this mystery thing is. We wish we knew what it was, but I'm telling you its identity is this. Okay, and it'll be hopefully clear what I mean in a second. All right, how do we see this? Well, let's take the NLSM. And let's just write down the Lagrangian. Okay, 1/2 J A mu J A mu plus pi A J A, where J A mu is the so-called chiral current. G inverse T mu G T A. Be very explicit. Okay, so G is some group element. G inverse G. This is the chiral current. Okay, so this is just another way of writing maybe the more familiar du dagger. Okay, same thing. I've also included a source term, capital J, for the pion, because I'm going to want to differentiate with respect to it to get amplitudes. Okay, I need to add sources. Okay, are we all good on this? Okay, this is. Yeah, there's a trace. Sorry, I summed on A's here. Yes, thank you. There's a trace here. Yes, thank you. Yes, thank you. Good. Now, what do we normally do when we compute? Well, we then pick a way, we pick a G in the sense that we have to choose how the pion is embedded in G. Okay, so more often than not, we would say e to the I pi over f, exponential map, say. Okay, that's fine. But there's more choices, of course. Okay, hopefully I've said this over and over in this set of lectures. There's an infinite number of choices of field redefinitions I can pick. So here's another one. This is called the Cayley parameterization. Okay, another way to parameterize this. These are not equal. I'm not saying they're equal, but these are different ways of embedding pi inside G. Okay, and they're related to each other by field redefinitions of the pion. Okay, so neither of these is right. They're just different coordinate choices. Okay, it's like any other scalar field theory. All right, any questions? Okay, now let's say you wanted to find the double copy in this theory. Well, here would be a poor way to do it. Just keep like field redefining pi, like searching for that right choice where like the Feynman rules satisfy everything you want and do your magic. Okay, you could just hunt, like keep changing coordinates and try to find that particular nice coordinate choice. But here's a better approach. Don't use pi. Use a more invariant variable, which is the chiral current itself. Okay, so the idea here is I'm going to reformulate pions, not in terms of the pion degree of freedom, but in terms of the much more invariant current, chiral current, that which the pion lives. Okay, so what do I mean by that? Well, I should also have said, in case it wasn't clear, you forgot, the equation of motion for this theory is well, let me write it here. The equation of motion for this theory is just that the chiral current is conserved. Okay, so the Euler-Lagrange equations of motion for pi tell you that that dj is 0. Okay, so let's just write that out. d mu j a mu equals j a. Okay, I'm keeping that source term. Okay, this is just the Euler-Lagrange equation of motion for that Lagrangian. Okay, now here's where the key move is. Okay, so we're going to define this theory a little differently. Forget that Lagrangian. Let me use another equation of motion, which will contain equivalent information as that, which is the statement that J is flat. Okay. Flat connection. Okay, because obviously J, if you just squinted, you'd be like, oh, J is some vector field, non-abelian vector field. It almost looks like it's in Lorentz gauge. Let me define it to be flat. Okay, this is my input. So these are my two defining equations for what's going to be the classical field theory of pions. Okay, what does this imply? Well, if J is flat, then it is equal to this. Okay, so if you like, that is an implicit equation, an equation that implicitly dictates and projects out everything except the pion degree of freedom inside J mu, right? Because this just says it's pure gauge. Okay, this is a gauge transformation. Okay, this is kind of the usual sense in which we think of pions as longitudinal modes of a gauge boson. Okay, but I'm inputting it by fixing this as a condition, a fixed condition on my theory. Okay, so these are my defining relations. Number 2 here implies this, and crucially, is agnostic about how I embedded pi inside G. In fact, in some sense, G and pi are born, but I never make reference to exactly how I embedded them, because I'm still going to deal just with J. Okay? All right, now, as it turns out, this set of equations was written down by Slavnov in like 1970. It's called a gauge invariant formulation of chiral perturbation theory, or field basis invariant formulation of chiral perturbation theory. He had no idea about the double copy, though. And that's the key next step, okay? Which is we're going to show you how I'm going to show you how double copy is already in these set of equations. How do I do that? Well, let me take the following combination of equations. d mu of equation 2, d mu of equation 1. Okay, what do I get? You get the following. Box j mu a plus f abc jb nu d nu jc mu equals d mu j a. Okay. Plus terms of order little j and capital J. I will get to these in a second. Well, actually, let me get to them now. Okay. So if you just combine these as an equation, you get. These are terms that are proportional to both the source term and the field. Okay. And I'm going to throw them out because I'm going to compute on-shell scattering amplitudes. And when you compute on-shell scattering amplitudes, these types of terms exactly correspond to the nonlinear parts of field redefinition. So you could add it, not add it, but when I do LSZ, these will be thrown out. Okay, if that's confusing, don't worry about it, I can explain after. But these are irrelevant if I care about solving this equation of motion to get tree amplitudes that are on-shell. Okay, now if it's confusing to you what I mean by solve equations of motion to get tree amplitudes, hopefully most people know what this means, but famously, if I give you an equation of motion with a source, if you solve perturbatively the one-point function in the field in the presence of the source, it's the generating functional for tree amplitudes. Okay, that's I think probably in like Shrednicki or something. Okay, or what, I forget which book. So that's the way I'm thinking about this equation of motion. Okay. Now let's stare at it. Okay, this if you didn't know better, you just walked in, had no idea this was about pions. What would you say? Well, this is a vector, an adjoint vector, with a box here. So it's got a 1 on p squared propagator. Okay. It's got an equation of motion with 2 j's here, which means it's a cubic interaction. Okay, so if this is the propagator, there's some cubic interaction on top of it. Okay, and then it's got some strange source. Okay. Any questions about the setup here? Okay. Now let's write Feynman rules for the pions using this setup. And okay, sorry, I should keep this. And I think the first thing you should worry about is like, wait a minute, I don't care about chiral currents. I'm trying to scatter pions. Why is this guy talking about chiral currents? It's invariant, but it's not the thing we want. Okay? Well, that's okay, because we can get pion amplitudes from this thing. Okay? Well, how do we get it from this thing? Well, j mu a is of course related to pi. In my notation here, at linearized order, it's just the pi field. So the one particle state inside J is derivative of pi. And there's other corrections here, pi squared and so on, which are all field basis dependent, okay, as I said. These dot dot dots correspond to whatever choices I happened to make here. Okay. Now, what I can do is just formally invert this equation. Okay, what do I mean by that? Well, like dot both sides by a vector and then solve for pi. Okay, it's clunky, but it does the job. Okay, so pi a, let's call this, this could be like a light cone type gauge if you like, that's what it looks like. J mu a over q partial, okay, in momentum space this would be q dot momentum. Okay, I'm formally inverting it, plus dot dot dot. Okay, why am I saying this? I'm saying this because if you can compute the one-point function for the chiral current, you can get the one-point function for the pion, and from the one-point function of the pion, you can extract the amplitude. Okay? And crucially, as I was saying there before also, these dot dot dots, as soon as they go in shell, since they're nonlinearities, nonlinearities in the field redefinition, I can set them to 0. Okay? So if you do this, you invert this, use that equation, and solve, you get a set of Feynman rules. Okay? Let me show you what those Feynman rules are, just so I can be very explicit. Okay, so the idea is like I have like a vector effectively. I have a vector, which is the chiral current, its propagator. I kind of wrote it schematically there, but let me write it out explicitly. A1, A2, eta mu1, mu2, because there's also a mu index, mu1, mu2, over p squared. Okay, so this p squared is going to form all those 1 on S, 1 on T, 1 on U terms, because every diagram is going to be cubic. Every diagram is cubic because there's only one cubic interaction. The cubic interaction looks like this, minus F, A1, A2, A3. It's actually pretty simple. P2, mu1, eta mu2, mu3, minus IP1, mu2, eta mu1, mu3. Okay, that's the vertex, 3-particle coupling. And then we have external polarizations. Where are these external polarizations coming from? They come from the fact that in this setup, my source term started out for pions, but in terms of this new field, it's the derivative of the pion, the derivative of this source, which is the source. So I get a p mu here. Okay? So the external polarizations are momenta. Okay? It's like I'm taking the longitudinal piece. Okay? So there's a polarization here, which terminates on legs, which is I p mu. Okay? And there's one last leg, which is this funny Q piece, but it's one more diagram. Let me even write it. There's one more type of polarization, which is this thing, which is Q mu over QP. Okay, that's not too important. Okay, but the point is, this set of diagrams gives you a bunch of cubic Feynman diagrams. Okay, the cubic Feynman diagrams look very much like Yang-Mills theory cubic interaction. The external polarizations are funny. Right? But when you add them up and compute, you'll get pion amplitudes, like the usual Cairo-Lagrangian pion amplitudes. Now, what's surprising about this? There's many things surprising. One, this has odd point interactions. Pions don't have odd point interactions. Pions come in even point only. What happens is that for any odd point, you find that they vanish magically. They cancel magically on shell. Okay, so the fact that the whatever G parity that is broken in this formalism is again evaporates in the final answer, so it obscures that. It also obscures the usual picture we have where we have d pi, pi to the n. Okay, right? An infinite tower of like higher and higher valence operators for pions. No, there's just one cubic. That's it. One cubic interaction. Okay, now I'm drawing these Feynman diagrams because if you compute them off shell, like in the middle of some tree diagram with all legs not conserving, not on shell, but off shell. So in other words, if you compute this diagram minus this diagram, you find that it equals this diagram. Okay, so where there's any blob here. Okay, so imagine this is like a internal, 4-point function sitting inside a Feynman diagram, computed with these Feynman rules. Okay, so those straight lines are these squiggly lines. You find that, okay, let me say it maybe, forget my signs here, but like this is equal to 0. Okay, it's like ns plus nt plus nu. These are explicit Feynman rules that automatically give the kinematic Jacobi identity. Okay. Now, what does that mean? That means that I can square the Feynman rules to get the Feynman rules of the new theory, which also means I can square the equation of motion, which I'm going to do in a second. Like I'm going to take equations of motion with fields and square them. Okay. But before I do that, let me try to still illuminate, because right now it may still seem magical. Okay. Why did this happen? Okay. As maybe a side note, I'll mention this is also the vertex that shows up in the Navier-Stokes equation. I'll let you stew on what that would mean. But it's also the vertex in the Navier-Stokes equation.
I'll just let you know it's about 10 minutes.
Cool. I think I'll probably be able to finish. Okay. The upshot is that this kinematic structure here, okay, is the momentum space version of, did I erase it? Yeah, it's gone. Momentum space version of the diff algebra. Okay, and to show you that, let me write it here so we can compare. Okay, this will be, rather than keep on rewriting, let me put side by side two of the theories that we've studied. Okay, so this here is, let's just erase this. This here is an LSM. Okay, what does biadjoint scalar look like in equations of motion? Okay, so you'll probably see it as soon as I write it. Okay, plus f a b c, f a bar b bar c bar, phi B bar phi CC bar equals J A bar. Okay, so this, of course, box is designed to be aligned. But what's the difference between these? Well, this A bar index apparently has become a mu index if I just squint at them. Similarly, these barred indices have all become vector indices. And this structure constant has generated a derivative. Okay? Now, if you just think a little bit, you'll realize what the rule is, which is exactly what I said at the top here, which is the following replacements. Okay? Take a theory with a colored object, let's say in the adjoint, and map it to v mu d mu. Okay? Send it to a vector. Okay? Color index gone. Replace the generator with a partial. Anytime you have f a b c times v b w c, replace it with the corresponding structure constant for the Lie bracket, right? Which we know that's v nu d mu w mu minus w nu d mu v mu. Okay, so I'm being very symbolic here. V could be any object. You could have more indices, other junk in play, but you just do this operation. Okay, and maybe it's the last piece. I'll also say you could take JA, the source, and you send it to d mu j. Okay, if you apply this operation to biadjoint scalar theory's equation of motion, you just do that, you get this equation. Okay, you essentially learn that this barred structure constant is the Lie bracket. Okay, so that's the mapping. Now, why was it guaranteed to work? Well, everything good about the original theory only cared about the antisymmetry of FABC and the Jacobi identities, which are all satisfied by the Lie bracket also. Okay, so that was all guaranteed. Now, we can kind of do this now for all types of theories, anything with a color, to get new novel representations of theories. Okay, so let me do, this will maybe be one of the last things I'll say. So let's say we took this theory, which is the theory of pions, and double copy it a second time. Okay, by this I mean take this FABC and replace that with Lie bracket. Okay, right? It's already, I went from, in fact, let me do it here. If you start from biadjoint scalar theory, take the barred color, replace it with diff, you get NLSM. If you go one more step, replace this one with a second Lie bracket, you get a set of equations of motion. Let me just write it. It's something that has absolutely no color, but it has two Lorentz indices. Okay, let me just write it out, and you can see for yourself if you so care that this is what you get. But J mu bar, d mu bar, J nu mu bar equals d mu bar J. Okay, I just did the same thing again. This thing is actually the Galilean. Okay, you can just check it. Okay, this is an equation of motion that had never been written down before, which describes the Galilean. Now, of course, Galilean is a scalar, but I have a tensor object, which I'm going to be computing Feynman diagrams for, and then dotting into weird polarizations. Just like for the pion, I had a vector floating around, dotted into weird polarizations to get a scalar. Okay? So I'm not saying there's an intrinsic spin 2 or spin 1 particle. I'm saying I've introduced a set of interesting auxiliary fields which totally manifest this property. Now the thing I'll finish with is kind of the last exotic case you can look at, which is Yang-Mills theory. Okay? I just told, in fact, let me leave this here. So, okay, I said I can do this to any theory with color. Yang-Mills has color. Let's do it to Yang-Mills. Okay? So what do I mean by that, like explicitly? Well, in Yang-Mills, I have a field strength F mu nu A, which is equal to D mu A nu A plus F A B C A mu B A nu C. Okay, and then I also have a field equation, yada yada yada. Okay, let me not write out all these things. Okay. What would happen? Okay, this is like an interesting question you might ask yourself. What would happen if you took the Yang-Mills equations of motion and just replaced the color algebra with the diff algebra? What is that? Okay, like very explicitly, you'll get a new field strength. Okay, so what that means is this color index becomes a Lorentz index. This becomes F mu nu. Okay, let's get this right. F mu nu mu bar equals d mu A new bar plus A new bar, D new bar, A new mu bar minus A. Okay, lots of indices. But if you just squint at it, you squint it at the bottom line, you kind of think like, oh, that's Yang-Mills, right? Like it's DA, DA, AA. Okay, sorry, DA, AA, AA, but there's like derivatives jammed in, and there's no color. Okay? But this is a theory. Okay? So if you do the same thing for the field equations, you get equations of motion for Born-Infeld theory. All right? So you could literally compute with these equations of motion perturbatively, and you'll get the Born-Infeld scattering amplitudes. Okay? So what I'm kind of saying here is that everything in this dictionary, okay, it's erased, on the scalar side, the scalar effective field theories, stem from this structure. Okay? If you like n, this thing I called n NLSM, the kinematic numerators that corresponded to pions, that's the diff algebra. Okay. Now we can do this beyond just, I mean, this is the simplest case of just taking the dynamics, the equations of motion and applying it. If you like, this is a proof. All orders in perturbation theory for the full S matrix of the double copy. That's one way of saying it, because I've squared equations of motion, which dictate all those higher n particle scattering amplitudes. But you can also apply this to conserve currents. Okay, maybe I won't do this. Actually, how much time do I have?
3 minutes.
3 minutes, perfect. So maybe I won't do this explicitly, but you could find a conserved current and double copy it this way. Okay. In fact, maybe I'll even say this story because it's kind of amusing. So if you look at biadroit scalar theory, there's a conserved current in biadroit scalar theory because this has two colors, right? So you could write down a current that looks like this: A, B bar, C bar, F A bar, B bar, C bar. Okay, in other words, the color current, right? Biadroit scalar has two global symmetries for each color. You keep calling it color, but it's really a flavor. And there's a conserved current. You can double copy this. How do you do it? Just take the structure constant and apply that mapping. Okay. Now, if you do that, you find something very interesting. You get a conserved current, which is a conserved current of the chiral Lagrangian, and it's actually related to the stress tensor. Okay, so it like links together through double copy currents and charges in various nutty ways. Okay. Now, everything I've done here is for equations of motion, so it's implicitly about classical physics. I haven't done anything at loop order. That turns out to be harder, but there are some things we've done in the extreme limit of low dimensions, d equals 2, which is maybe fine, but d equals 2, where you can understand all this at the level of the Lagrangian. Okay, so the idea is you can build a Lagrangian where these symmetries all act mechanically. As it turns out, the theories being mapped onto each other are the 2D nonlinear sigma model, which is the principal chiral model, and the 2D Galilean, which is also another integrable theory. And there's a mapping between them that maps their integrable charges. The whole tower of things that are nice about those theories map onto each other. You can build classical solutions and double copy them. There's a huge kind of cool story there. And it works in low dimensions. But in higher dimensions, I think there's still a question, how do we put this into an engine of a real Lagrangian, not just the equations of motion, which I think is still an important open question. More to the point, gauge gravity, I still feel personally there isn't something as clean and nice as this. And I still would say, maybe as I end here, that the stakes are pretty high, okay? I said this before, but I really do think they're high. If you honestly think, and hopefully I've convinced you, that perturbative gravitational objects can be written as square root of gauge theory, and that's a weak duality, and you think that you can understand it at the level of Lagrangian, okay? And in this case, we can. I should also have mentioned we can do this also in ADS and DS. We did this in other cases because we know what we're doing. If you can start extending it, your kind of maximal dream is that this double copy would be true in arbitrary backgrounds, non-perturbatively. Okay. Obviously, if that was true, it'd be a gold mine because you could ask any crazy question in gravity and get an answer in a gauge theory. I don't think that's going to be true. I think that's too strong. It just doesn't seem, it seems too strong of a statement. But a much weaker statement that would still be interesting is if it's all true classically and at tree level. Okay? Let's say it's true that all classical GR observables are gauge theory observables. Okay? What that means is, indeed, numerical relativity is secretly the square of some classical calculation to be found. And just understanding that piece of physics is still like a big open mystery. Okay, so here right at the end, let me just say, well, thank you for listening, but also I hope that I conveyed at least a tiny tip of the iceberg as to why Amplitudes people are interested. It's like the closest you can be to the front lines. Like you're like staring at objects and being like, is this nice looking? Is this telling me something? There's something really workmanlike and like, I don't know, it's like you feel like you're right up against the physics trying to figure something out. Some of it could be illusory, certainly. Like there's that risk, like maybe these structures mean nothing. But I don't know, maybe they mean something. So hopefully, whatever, next time if I ever come back to Tassie, I'll come back and sleep in one of those small beds and tell you how we figured out everything. When I'm an old man, and I won't be able to get up on top of that bed anymore. All right, thank you. Yes.
I mean, so to what extent could string theory be an explanation for the gauge and gravity relationship here?
Right.
KLT decades ago.
For sure.
I know you said
Right.
can't be generalized in every direction, but
Good.
there it's open
Good.
and closed strings in
Good.
the relationship that underlies.
Very good. So the question was, can string theory just explain all this? Okay. And indeed, for gauge theory and gravity, it originated it. So of course, there's an explanation within it. It doesn't say anything about the kinematic algebra, of course, and so on. But let me kind of like harp on that fact a bit. Okay. So one thing string theory can't explain, I know for sure, is pi n squared goes to Galilean. Here's my one-liner. Okay. And they actually connects with other things I've said. Turns out in the Galilean, had this coupling dd phi to the n. It is actually missing a term, d phi to the fourth. In fact, this term is forbidden by symmetry. But you'll notice in my last lecture, I told you, this needs a non-zero coefficient in any ultraviolet complete consistent theory. We proved it. It has to be positive. Okay? The Galilean doesn't have that property, which is why it's sick. Okay? I should have mentioned that when we were talking about these bounds. But indeed, it's a strange toy theory. This is partly why massive gravity has its issues. It's related. But this isn't going to be UV completed in string theory in like a kind of canonical, sensible way because it violates positive dispersion relations, okay, which presumably string theory accords with those UV boundary conditions. For gauge and gravity, you could think that there's some explanation. But here's what I would say as a field theorist. If you have something which is true for so many field theories, like beyond gauge, gravity, pions, and it's not different instructions, it's literally the same instructions, maybe we have to put in a string theory, compactify, send alpha prime to 0 to do it. But wouldn't that be weird? I don't know. Wouldn't that be sad? We don't need string theory to tell us that there is an anti-gravity, that that anomalies cancel. You can use string theory to tell you that, but we don't need string theory to tell us that. So I want there to be, at least for my own happiness, a QFT explanation. It could be that we just have to ask Ed Witten how this works, and he'll tell us. That's often the way this works out. But yeah, I'm going to try anyway. But it's a fair point. Maybe it's all in string theory. Maybe the only way to explain this feature is to embed it inside another theory and then take a parameter to 0. It's possible. Yeah. I mean that seriously. It could just be the way to understand it. Yeah.
Is there a way to see, if you map between two theories and one of them is non-normalizable, is there a way to see that at the level of this double copy?
That's a great question. Okay. So you'll already notice that double copy doesn't preserve ultraviolet properties, right? Because Yang-Mills is asymptotically free. Gravity has horrible ultraviolet divergences. So I didn't talk about loops at all. But once you start talking about renormalization and radiative corrections, the way double copy works is at the level of integrands. So before you integrate, there are these integrands that are the analogs of trees, and those are the things that double copy and square. And then once you integrate, all hell breaks loose. So there's kind of a disconnect because all the nice structures are before you're getting a real final answer, which kind of makes this structure itself confusing, right? Because it's not a property of the final, real S matrix element after integration. There's other things I could say too related to higher dimension operators and how they're renormalized. But maybe that will suffice for now. Is that okay? Yeah.
All right, well, this is the last of Cliff's lectures, so let's have one more round of applause for the whole lecture series. We'll see you back at 3:45. This was a great series. Thank you very much.
Glad you enjoyed it. Yeah. Something for everyone. Thank you.